You got an object, mass m, you lift it some distance h, and the work done mgh. So that's going to be the change in potential energy. So that's why we often say potential energy is mgh. But, and this is a big but here, this assumes that the force is a constant mg. And that's very close to being accurate near the surface of the Earth. But when you're a long ways from the planet, the force of gravity is considerably different than it is near the planet. And so that makes this a much more complicated sort of scenario. So what would be the potential energy in this case? It's not because it's not a constant, it's not going to be equal to mgh. Okay, so because the force is not constant, so we have to do something different. And so we say, okay, so we got an object right here, and here we are, at some point, and this is like r1 away from it, and I want to go out here to some r2. Okay, so I know that I got to do work. Now we know that work is integral f dot dx. Now we could actually be more complicated than this even. We could say that we started here and we wanted to go out to here. So what we do is, in this case, we would do the integral, and this is actually integral, a path integral, f dot dx. So we'll do this path right here, and then we'll do that path right there. So that's path 1 and path 2. So integral f dot dx. Okay, that's path 1 and path 2. Now, the nice thing is that because the force that we have to exert to keep there's no actual force we have to push in that direction, because the force of gravity is towards the planet, so we're having to pull outwards, we're moving horizontally, so that means the dot product is 0. Integration by obliteration. Okay, so we don't have to do the integral at all. So all we have to do is worry about going straight out. You do not change potential energy staying at the same height. So that's why this first term is going to be 0. Okay, so now the work is going to be the integral of f dot dx, and we are going now from some r1 out to some r2. So we're having to exert a force in that direction to push it outwards, because gravity is trying to pull this way. Okay, so we think about that and we say, well, the force of gravity, force due to gravity, is going to be equal to g m over r squared, where we have this little m right here and big M right there. Okay. All right. So that's the force due to gravity. And so if I'm going straight out, then my dx is going to be dr. So that means that I'm pushing straight out. I'm going straight out because I have to push against gravity. Remember, the force of gravity is going to be inward, so I have to push outwards. And so that means this becomes integral g m over r squared dr. Okay. Well, that's straightforward, because g, m, and m are all constant, so it's integral of dr over r squared from r1 to r2. Okay, well, we know how to do that integral. What's the integral dr over r squared? Well, that's going to be equal to minus 1 over r. Okay, so that means that what we have here is that the work done is gmm 1 over r evaluated from r1 to r2. So, or negative for that. Okay, so that's going to be equal to, after we do some algebra here, gmm 1 over r1 minus 1 over r2. Okay. So that's the work done. So that's going to be the change in potential energy. gmm 1 over r1 to 1 over R2. Okay. 1 over R1 minus 1 over R2. So there's the work done. There's the change in potential energy. So now we say, well, let's think about this. Let's think about it and say, well, the change in potential energy. So if we've got Earth or some planet right here, and I'm going out here, let's take a limit as R2 goes to infinity. Okay, so if you take the limit as R2 goes to infinity, then the work done is going to be equal to GMM over R1. Okay, so that's the work done. Now, then you think about it and say, well, if we go out here, what's the potential for interaction in infinity? Well, you'd say that potential for interaction is pretty much zero. So we could define the U at infinity to be equal to zero. So that's a definition. So we define it that way. Remember, you can put the zero anywhere you want. So we'll say that the potential energy at infinity is zero. Work is change in potential energy. And so that means that we had to increase by GMM over R1 in order to get to zero. That would mean that my initial potential energy was minus GMM over R1. Okay, let's forget the R1 and R2 because, it's like we're infinitely far away, so let's just call it R. Okay, so this is my potential energy right here. So you notice if you were to look at that and graph it, you have potential energy versus R. Okay, now you start at the surface of an object, and so as you go, then what happens is it's negative. So as it's negative here, okay, that means it asymptotically approaches zero. So we would imagine if you do this in 3 dimensions in all different directions, this is like a big well, and that's why we refer to this as a potential well. You've all seen these pictures of black holes, that look like these funnels and sort of thing. That's an attempt of showing a two-dimensional or a two-dimensional drawing of a three-dimensional representation of a two-dimensional projection of a three-dimensional field in a well. I hate those things because it's like, what the heck are you trying to show? Because you're trying to do in 2 dimensions something that's 3 dimensions representing 2 dimensions representing 3 dimensions, and that's just silly. Okay, so but we can now say that the gravitational potential minus G M1 M2 over R squared. Okay, so this is the gravitational potential energy between two things.